All right, folks, continuing on here in chapter 6, the next section, section 6.2, we're going to talk briefly about area, and that will lead us to the definite integral, and we'll conclude the section with a pretty big theorem. It's called the fundamental theorem of calculus. It'll be with us for, the rest of our time in calculus. So here are the objectives we're going to look at in section 6.2. Objective 1, where we're just going to look at how to approximate the area under a curve using rectangles. Objective 2 will be to write a definite integral to represent an area. Objective 4 is the fundamental theorem of calculus. And then objective 5, we're going to practice using the fundamental theorem of calculus to evaluate definite integrals. So we got some really important stuff coming up here in this section. We've already seen one of the big topics in calculus, the concept of rate of change and instantaneous rate of change. And we know the slope of a tangent line gives us an instantaneous rate of change, and that's related to the derivative. The other big major topic in the study of calculus, it's the concept of finding area under a curve on a closed interval from A to B. So if we look at this generic graph of some function, it's that shaded region. Finding the area that's below the graph of f, above the x-axis, from A to B. So there was a big topic in calculus. How do we find that area? Now we know there are formulas in geometry that can help find area of certain figures, like triangles and circles, rectangles, etc. But there's no formula in geometry that would tell us the area of that shaded region that we see in that figure. This is where calculus comes in. So we're going to, what we're going to do though here initially is just talk about how we could approximate that area using rectangles, because we know the formula to find area of a rectangle, base times height. So here's the game that we're going to play. We're going to start off by dividing the closed interval into n parts called subintervals. So if you look at the interval there in that figure from A to B, we're going to just slice it into smaller pieces called subintervals. And the width of each subinterval, we're going to call that a step size, and we're going to go ahead and denote that by delta x. And that's going to match up with the width of a rectangle. So for any closed interval AB, when we divide it into n equally spaced subintervals, the step size, which is denoted delta x, is given by, delta x is nothing more than the length of the interval AB divided by the number of subintervals. So if the interval AB is the interval, say A is 1 and B is 9, so we're looking at going from 1 to 9. Well, that has a length of 8 units. 9 minus 1 is 8. B minus A, 9 minus 1 is 8. And, let's say we wanted to put in 16 subintervals. So n would be 16. So we'd have 8 over 16, which is 1/2. So if you have 16 subintervals in an interval that has a length of 8, well, of course, each one would measure a delta x value of 1/2, and that's what the step size is. Now, we're not going to do anything as large as that in our explanation here. We're just going to look at the function x squared minus 2x plus 10 on a smaller interval, 1 to 4. Notice the length of that interval, 1 to 4. It would have a length of 3. So A is 1, B is 4, so 4 minus 1 is 3. And then we're going to just use 3 rectangles. By using 3 rectangles, each would have a base of 1 unit. And we're going to use that to approximate the area under the curve of the function. So let's look at a picture of what that looks like. So there's a picture of what it would look like. You see the function x squared minus 2x plus 10. There's its graph. We see the interval 1 to 4. There are 3 rectangles in there. Each rectangle has a base of 1, and we see the height of each rectangle. And let's go to the next slide. Oh, but before we go to the next slide, I did want to stress one more time the left endpoints of a subinterval. That's what was used to draw the rectangles. What I mean by draw the rectangles, look at the subinterval from 1 to 2. The left endpoint of that subinterval is 1. And it's that value of x equals 1 that was telling us the height of the rectangle. And we would actually get the height of that first rectangle by evaluating the function at 1, just doing f of 1. When you look at the second rectangle, and it's the rectangle that, its base is going from 2 to 3, that's a base of 1. Notice the height of that rectangle. That would be found by evaluating the function at 2. And then the third rectangle, the base is from 3 to 4, which has a base of 1. The height of that third rectangle, it would be found by evaluating the function at 3. So there's the graph again, one more time. We can find the area of each rectangle. It's just simply base times height. And we can use the area of each rectangle. We can approximate the area under the curve. In other words, we can find the area of each one of those rectangles, add those 3 rectangular areas together, and that sum would give us an approximation to the area under the curve. But it looks like from the picture that approximation, adding up the area of those 3 rectangles, it looks like it would be an under approximation. I mean, there are some pieces that are missing there. Now, since we use the left endpoint of each subinterval to determine the height of the rectangle, this picture is demonstrating what is called the left sum method, using left endpoints to give the height of a rectangle. Notice one more time that the height of each rectangle is found by evaluating the function at the left endpoint of each subinterval. In other words, the first rectangle has a height of f of 1. The second rectangle has a height of f of 2. The third rectangle has a height of f of 3. And then we would take the base, and each rectangle has a base of 1, multiply it by the height of each rectangle. That would give us the area. Now, before I go to the next slide, I do want to mention that we could use the right endpoints of each subinterval to tell us the height of a rectangle. So we could have used 3 rectangles where f of 2 would give us the height of the first rectangle, f of 3 would give us the height of the second rectangle, then f of 4 would give us the height of the third rectangle. And when we do that, that method is called the right sum method. And I'm going to briefly go over that in a minute. So here's the left sum method. If you have a continuous function, y equals f of x, that's defined on a closed interval a, b, we can go through the process of computing the left sum using n equally spaced subintervals by employing the following steps. Step 1, compute the step size, delta x. We just talked about how that is nothing more than b minus a over n. Step 2, find these x coordinates of the left endpoints of each subinterval. You would start at x of 0 equals a, and then just successively add the step size, delta x. Step 3, here's what we do to compute the left sum. I mean, look at this mess. You'd have the area of the first rectangle plus the area of the second rectangle plus the area of the third rectangle plus, yada, 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 plus the area of the nth rectangle. And, in doing that, on the next line down, the area of the first rectangle is delta x times f of x sub 0. Keep in mind, that's nothing more than saying base times height. The area of the second rectangle is delta x times f of x sub 1. That's basically just saying base times height, and etc. I do want to talk about these last two expressions that you see. It's using what's called summation notation. Keep in mind, it's expressing nothing more than you're adding up a bunch of areas. So f of x sub I, that is the height of a rectangle. Delta x is the base of a rectangle. So when you take those two quantities and multiply them together, it gives you the area of a rectangle. The sigma sign, that means summation. It means you're just adding up a bunch of rectangular areas. So real quickly, the right sum method, it's just like the left sum method. It starts off looking the same. The differences in step 2 here, you find the x-coordinates of the right endpoints of each subinterval, where you start with a plus delta x. So that would be where the first rectangle would start, a plus delta x. And everything else is going to look the same. Area, finding area of rectangles, summation here at the very end, the last two expressions. Again, f of x sub I times delta x, that's just the height of a rectangle times the base of a rectangle, which gives you the area of a rectangle. So don't be concerned I'm going through this, kind of quickly. It's just kind of giving a very quick, brief overview of what would be rectangular approximations. We're going to see a much better way to do it here in a minute. Here I'm saying as the number of rectangles gets larger, in other words, as you start to put more and more rectangles under the curve, what we started off with, we just looked at 3 rectangles. Well, if on that same interval you decide to put in 30 rectangles, or then 300 rectangles, then 30,000 rectangles, 30 million rectangles. So as you let the number of rectangles approach infinity, that's n approaches infinity, the approximations using rectangles and adding up the area of all those rectangles, well, they actually start to approach the actual area. And so here's our area under a curve formula. This isn't going to be something that you have to memorize. If f is a continuous function defined on a closed interval AB, then the area under the graph of f from A to B, it's given by this mess. Well, you notice at the very end, I just want to talk about the very end, what we see here. The limit as n approaches infinity, the sum from I equals 1 to n, f of x sub I times delta x sub I. So again, we know f of x sub I times delta x sub I. F of x sub I is the height of a rectangle. Delta x sub I is the base of a rectangle. So height times base is area. Sigma means add up a bunch of areas. The limit means limit as n goes to infinity. That means we're letting the number of rectangles approach infinity. Now that looks like a pretty serious, hardcore formula for area under a curve. So I just want to kind of focus on the core of what that last expression says. It's saying limit of a sum, that the area is nothing more than a limit of a sum. You don't have to memorize that formula, but I would just like you to kind of remember it's a limit of a sum. Now that limit of a sum it's much better to represent that limit of a sum with what is called a definite integral. So for a continuous function f, the definite integral of f on the interval ab is, and I'll read that, we read that as the integral from a to b f of x dx. And the definite integral is defined to be the limit of a sum. A and b are called the limits of integration. So what's different here from what we saw in the previous section? In the previous section, we saw the indefinite integral. Now we have the definite integral. In the definite integral, a and b, there are going to be numbers there. So let's look at a quick example. Write a definite integral to represent the shaded area. All right, so here's the graph of a function. The function is negative x squared over 2 plus 8x minus 17. So we see its graph. You see the region that's shaded here. It looks like it goes from an x value of 4 to an x value of 12. So we need to be able to write a definite integral that just represents that shaded area. So I think we're going to have the integral sign. A is 4, b is 12. So the lower limit of integration should be a 4. The upper limit of integration should be a 12. F of x, well, we see what f of x is, negative x squared over 2 plus 8x minus 17, then dx. So we should have something like this. The integral from 4 to 12 of negative x squared over 2 plus 8x minus 17 dx. So that's the definite integral that represents the area of that shaded region. And here in a minute, we are going to see how we can evaluate that definite integral, what we can do, how we can come up with the exact area. So I hope that makes sense. Pretty easy process to represent shaded area as a definite integral. Real quickly, I do want to talk about some properties of the definite integral. So first off, all those properties we saw in section 6.1 on the indefinite integral, properties such as the constant multiple rule, the sum difference rule, they're still true. They're true for definite integrals. Number 2 is a very special property. So we can look at this figure here. It looks a little blurry. I apologize for that. But if you're looking at that function and you're looking at the shaded region from a to b, this property called the interval addition rule says you can pick any value c that's between a and b, and you can split the integration into two pieces. So in other words, the integral from a to b of f of x dx is equal to integrating from a to c f of x dx plus integrating from c to b f of x dx. Intuitively, that should make sense. If you look at the area of the shaded region from a to b, that area should equal the area from a to c plus the area from c to b. And that, in short, is the interval addition rule. Then the third property is if you ever have to integrate from a to a any function dx, well, the value of that definite integral is 0. So if your lower limit of integration and upper limit of integration are the same number, it doesn't matter what the integrand is. The value of that definite integral is 0. So now how are we going to evaluate definite integrals in general? Well, we use this thing called the fundamental theorem of calculus. Pretty important theorem coming up. If f is a continuous function defined on a closed interval ab, and big F is an antiderivative of little f, then the definite integral from a to b of f of x dx equals uppercase F evaluated at b minus uppercase F evaluated at a. In other words, get an antiderivative. That's what big F is. and you're just going to evaluate the antiderivative at b minus evaluating the antiderivative at a. The definite integral from a to b of f of x dx, it is the definite integral of f on the interval a to b. And then 2, I'm mentioning again, a and b are collectively called the limits of integration. Just remember, a is the lower limit of integration, b is the upper limit of integration. A, it's the same a as that's in the square brackets there, the interval a to b. Those a's are the same and the b's are the same. A couple of key points on the fundamental theorem of calculus. Key point number 1, it is important to kind of understand that, this gives us the area under the graph of a function from x equals a to x equals b. It's a special case of the fundamental theorem of calculus. It tells us the area when our function is greater than or equal to 0 everywhere on the interval a to b. So in other words, the graph on the interval a to b doesn't go below the x-axis. Number 2, not frequently, all the time, we're going to be writing that difference, f of b minus f of a. We're going to write it as f of x vertical bar a to b. And this will be, I'll demonstrate all this when we finally do an example, which is right now. So in this example, we're going to evaluate some definite integrals using the fundamental theorem of calculus. And we're going to evaluate, you see what a is, you see what b is. So we're gonna work these out on the chalkboard. So I'm getting ready to head to the chalkboard to show you how to evaluate definite integrals using the fundamental theorem of calculus. All right, here we are going to work out this example where we are evaluating a definite integral using the fundamental theorem of calculus. A really important theorem that's going to be with you for the rest of Chapter 6 and Chapter 7. It's the rest of the time in calculus. So one more time, here's how you read this. This is a definite integral. You read it as the integral from 3 to 6 of 2x squared plus 5 dx. 3 is the lower limit of integration. 6 is the upper limit of integration. It's telling you the interval from 3 to 6 on the x-axis, the interval from 3 to 6. So here's what you do. You do just like you did in section 6.1. Get an antiderivative for 2x squared plus 5. So the antiderivative for 2x squared plus 5 is 2/3 x cubed plus 5x. That's the antiderivative. That's that uppercase f of x. And then we put a vertical bar, lower limit of integration, upper limit of integration. So this is the antiderivative, the big f of x. We're evaluating it from 3 to 6. So it says to start off, you evaluate the antiderivative at 6. So that would look like this. 2/3 times 6 cubed plus 5 times 6. That's evaluating the antiderivative at 6 minus, now the 3 goes in. 2/3 times a 3 cubed plus a 5 times 3. So all of this here, this is f of 6. This is f of 3. So now it just becomes an arithmetic problem, just kind of, doing all of this arithmetic. And if you do it correctly, I would use my calculator, you're going to end up with a value of 141. Okay, so first thing, in section 6.1, when we dealt with indefinite integrals, we ended up with the function, an antiderivative, plus c. With the definite integral, we're getting a number as an answer. So if you're wondering, for this antiderivative, why didn't Bill put a plus c there? Well, think about it. If I did have a plus c, there would be a plus c in here, there would be a plus c in here. Subtract, they would cancel out. Think of it another way. It doesn't matter what antiderivative you have here. You could pick your favorite constant. You could say 2/3 x cubed plus 5x plus 17, if you like 17, the number 17. You'd have a plus 17 here. You'd have a plus 17 here. The 17 minus the 17 is 0. That constant's going to cancel out when you evaluate it with the fundamental theorem of calculus. So for that reason, don't even bother putting a constant. When you get an antiderivative here, don't worry about a constant. That's only when dealing with a definite integral. You don't worry about the constant. So the value of this definite integral, the integral from 3 to 6, 2x squared plus 5 dx, we evaluated it with the fundamental theorem of calculus, and we came up with 141. Let's try the one we have over here in part B. Integrate from 4 to 6, square root x minus 4x dx. So we have to begin this evaluating this definite integral using the fundamental theorem of calculus. We have to begin by getting an antiderivative. So I would start actually with some algebra, rewriting the square root as x to the 1/2. Okay, now I get an antiderivative for x to the 1/2 minus 4x. So antiderivative of x to the 1/2, well, that's 2/3 x to the 3/2. Antiderivative of 4x is 2x squared. Make my vertical bar, put my limits of integration on. So remember to evaluate this now with the fundamental theorem of calculus. 16 comes in for the x's first. So now you give us something like this. 2/3 times 16 to the 3/2 minus 2 times 16 squared minus, now the 4 goes in. So 2/3 times 4 to the 3/2 minus 2 times a 4 squared. And then if you evaluate this correctly, you're going to end up getting, oh boy, negative 1,328 over 3. Or as a decimal, it's negative 442.6, and the 6 is repeating. All right, I want you to practice a few of these right now. So let's see. Right now, why don't you do number in section 6.2, why don't you do number 35, number 39, and number 45. So go ahead and pause the video, do these 3, and then after you've done those 3, restart the video, and I'll be here at the chalkboard, and I'll work through each one of them to make sure you have the correct answer. All right, here we go. Let's make sure that you got numbers 35, 39, and 45 correct. So number 35, integrating from 3 to 5, 2x minus 1 dx. So I get an antiderivative for 2x minus 1. The antiderivative is x squared minus x. So I have to evaluate that from 3 to 5. So remember when I evaluated from 3 to 5, the 5 comes in first. So when I put the 5 in, I get 5 squared minus 5. So that's 25 minus 5. Then the 3 goes in, so I'd have 3 squared minus 3. Well, 3 squared is 9 minus 3. And see, what is this? 20 minus 6, so I get 14. as the value of that definite integral using the fundamental theorem of calculus. So hopefully you got 14. For number 35, we're integrating from -1 to 2, 4 minus x squared dx. So I start off by getting an antiderivative. I have an antiderivative of 4x minus 1/3 x cubed. Evaluate that from -1 to 2. So remember, when I evaluate using the fundamental theorem of calculus, the 2 comes in for the x's first. So 4 times 2 is 8. 2 cubed, well, 2 cubed is 8, so 1/3 times 8 is 8/3. Minus, okay, now the -1 comes in. 4 times -1, -4. -1 cubed is -1. So that would be a -1/3 minus a negative. So that's a plus 1/3. And if I do 8 minus 8/3 minus the quantity, -4 plus 1/3, I'll end up getting a value of 9. So hopefully for 39, you got a value of 9. 45. Well, here we're getting some decimals involved, but it doesn't change the process. You know, to get an antiderivative for the first term here, I would have 0.2 over 3 x cubed plus antiderivative for the second term, 1.3 over 2 x squared. Antiderivative there's a 2.3x. And I got to evaluate that from 0 to 5. Okay, well, So the 5 comes in for the x's first. Make kind of a mess there. Notice when the 0 goes in for the x's, I'm just going to get a 0, and a 0. Well, that's kind of nice. So put my 5 in for the x's, and well, let's see, 0.2 over 3 times a 5 cubed plus 1.3 over 2 times a 5 squared plus 2.3 times 5 minus 0 plus 0 plus 0 is 0. So that's kind of nice. When I use my calculator, I would use a calculator on this, I end up getting 433 over 12. Or if you have it as a decimal, 36.083, and the 3's are repeating. So there were, did 2 examples evaluating a definite integral with the fundamental theorem of calculus. 3 of the homework problems that you should have practiced immediately, right now, of evaluating a definite integral using the fundamental theorem of calculus. And that's all the homework. That's all the homework is going to focus on in section 6.2, evaluating definite integrals with the fundamental theorem of calculus. So that ends what we're going to do here in section 6.2. So at this time, go do the homework in section 6.2. Thanks for watching.